Okay, so hopefully you just saw how you can use polling to do I/O and deal with the slow input-output. But because of the vast differences in speeds of I/O or input-output versus the CPU, which is very fast, it's not good use of the CPU to do repeated polling. And so instead of repeated polling, the operating system can do something like issue a request, send a command, and then say, okay, this is going to take a long time, so I'm going to wait for that I/O to finish and switch to another task. And so this is typically what happens in CPUs these days, is if you have to do any kind of file I/O, you say, okay, I'll wait for that thing to happen. I'm going to do a context switch and schedule some other process that is ready to run and not doing I/O, and I'll run that while I wait for that slow I/O to be finished. When that slow I/O device is finished with that operation, it does this thing called, it raises a hardware interrupt. And so it's actually, it used to be just a electrical signal. That's why it's called a hardware interrupt. There was an actual electrical signal that says, okay, this interrupt request line has gone high, or it's active, and that causes the CPU to finish its current instruction and then check the interrupt, and it'll find that that line has gone up, that hardware interrupt request line has gone up, it's active, and so it'll say, okay, I need to handle what I'm seeing now from this device, and it'll put the program counter on the stack. It will say, okay, jump to this interrupt service routine. I'm hoping that you've seen some of this. We won't really get into the details of this because really we want to concentrate on the slow I/O part. How do we deal with that? Okay, so the rough idea is that you get this hardware interrupt, you cause the CPU to jump into this interrupt handler. There's a lot that happens in here. This handler is part of a device driver that the operating system loads into memory, and so the operating system, it's considered part of the operating system code that will handle any kind of event from devices in general. For example, reading data from a hard drive or writing data to a hard drive. And then once it's done, it'll wake up that process waiting for the I/O. So why are we doing all of this? Isn't this more work? No, it turns out that you can make better use of the CPU if you do interrupt-driven I/O. And so we'll take a look at that next. So here's a schematic view of what's happening. So process 1 is running in the CPU. So many cycles, and then all of a sudden it has to do I/O, and if it uses polling, then it's just sitting in that while loop. Is the device ready? No. Is the device ready? No. And this goes on for potentially millions of cycles, while the disk device is handling this event from process 1. The disk is busy trying to write this as fast as it can, but it's very slow, and so the CPU is just sitting there in that loop, basically checking, is the status changed. And then once it's done, millions of cycles later, the CPU says, okay, it's done, I can do something else now. So rather than doing this is very inefficient use of the CPU. You can do this. It's not unreasonable. Sometimes you have very fast I/O, but if it's slow, it's not good use of the CPU, and you would switch to doing something like interrupts. And so with interrupts, the picture is slightly different in that here you are processing, you're running process 1, you issue an I/O request, and you instantly process 1 is blocked. It's considered as being blocked for I/O, and you say, okay, let me know when you're ready, and the disk will go ahead and do the work for one. In the meantime, since that's a long wait, you can schedule something else like process 2 starts to run and can get some useful work done. And then once that IO device, let's say it's a disk, is ready, it'll do the interrupt and say, okay, I'm ready now. And then you'll quickly finish up whatever you're doing with process 2, do context switch, put the PC on the stack and all of that, and then say, okay, it's time to handle this interrupt, and you handle the interrupt and you say, okay, this data is ready, and then process 1 can pick up again. So the big picture is just that instead of spending time sitting in a loop checking if some device has changed its status, you switch and do something useful, something different, a different process. So anytime you have to do IO, that's what the scheduler knows. Okay, this is going to take a long time. Let's do something else. All right. So when you have to write large amounts of data, let's say a whole block, which could be, let's say 512 bytes or maybe even 4096 bytes, that's a lot of memory that you have to copy over to the device. So the CPU will have to spend time doing that copying. So it takes a byte, copy it to the device, wait for it to be done, write another byte, and so on 512 times. And then let's say you copy all of that into the memory of the device. We haven't really talked about how that works, but just assume that it does. You write a whole bunch of memory to the device, and then you say, okay, go ahead now and write that entire set of 512 bytes to some location on the drive, and that's when you would be blocked for IO and some other process can run. And then once it's done writing, once the disk is run writing all of those 512 bytes or whatever, it can send an interrupt and say, okay, I'm ready, and process 1 can pick up where it left off and continue. Okay, so hope that is clear. All you're doing is, let's say, writing a whole bunch of things to a disk. You have to copy this, tell a disk to go ahead and write the data to the disk, and then once it's ready, the disk will send an interrupt. Okay, the write is done, and you can continue where you left off. So now the problem is, sure, you're making good use of the CPU, but copying all that data from RAM to the controller is also not great use of the CPU. Your CPU is doing, like sort of tedious tasks that it could be using that time for something better. So is there an alternative to having the CPU busily copying this data from RAM, from the CPU's RAM, to the memory of the disk, and then telling it, okay, go ahead and write it? And actually there is special hardware that will allow you to just take over the manual, the tedious duties of copying stuff from memory, from the system memory to the disk memory. And it's called direct memory access, or DMA. We'll refer to this as DMA from now on. So when you say DMA, chances are we're talking about direct memory access. And so there's actual special hardware. There's a chip usually that does things like direct memory access control. All it does is copy stuff from system memory to a device, or from device to system memory. So when you do a DMA data transfer, what you're doing is you're copying data to the system memory from device memory, or the other way around. Either way, it can do both. And so the big picture is, here it is. You say the CPU is processing, it's running process 1, and then figures out, okay, I need to transfer 512 bytes from memory to the disk. You tell the DMA controller, okay, copy these 512 bytes to the disk, and this DMA controller that's all it does, is copy bytes, and while it's doing that, the CPU can switch to context switch to process 2 and have more time to work on quote unquote more important things like running other processes rather than just manually writing bytes to an IO device. Okay, so at this point you have not only the CPU active, but also the DMA controller is active, and it tells it, the CPU tells the DMA controller where the data is in RAM and which device to transfer the data to. It goes off and does this while the CPU can do more useful work. So the DMA controller starts this transfer and then waits for this thing to be done and interrupts the CPU when it's done, and then the operating system sends a write to the device, and then the device spends whatever time writing. It's very slow, and then when it's done, it sends an interrupt and says, okay, this writing is done, and then the CPU can switch back to process 1 if it's ready. Okay, so it's much better use of CPU time to be basically running the code in processes rather than doing tedious work like copying memory. So instead of having the CPU execute a loop to copy this data to a slow device, the DMA controller bypasses all of that, take care of the copying, sort of takes the load off the CPU. And so this allows the CPU to switch to some other useful thing, like some other process that's waiting to run, and this is much better overall CPU utilization. That's the main advantage of adding this little piece of hardware for the DMA controller, and it makes everything much faster. So next up, we have to wonder, well, interrupts go from devices to the CPU. How does the CPU communicate with the IO devices? Are there special instructions that the CPU can use? It turns out yes. There has been in many generations of CPUs, there have been special instructions. But then those special instructions turn out to be, maybe not the best way to communicate with these devices. And it turns out there are alternatives. And the one that we will look at is memory mapped I/O. So we'll take a look at both of these next. As far as explicit CPU instructions, you probably have seen this at some point in previous courses, but the Intel x86 CPU has these in and out instructions that communicate with specific device ports, and so you have to use ports. And so older CPUs like in IBM mainframes also had these kind of explicit I/O instructions. So these were instructions in the instruction set of the CPU just to do I/O. And so what this allowed the OS to do is to send data to I/O devices and to carry out the steps that we talked about earlier. That is, write a whole bunch of things to the register, various registers, read from those registers to figure out what the status of the device is. So when we say, check the status of the register, we're actually doing this in instruction. That's how that communication happens. An alternative to that is, rather than having specific instructions, you can use just memory reads and writes. That is, just pretend that you're writing to memory, but it's actually a device. And that's called memory mapped I/O. So you can make the hardware of the entire system have these device registers. We talked about those before, the status, command, and data, and make them appear as if they were memory locations. That is, even though you're actually doing I/O, you can actually map those registers to somewhere in your memory, to the process address space. And usually it's a low address location. And so to access a device register now with this memory mapped I/O, what all the OS does is actually just write to memory, but it's actually not memory. It is a register on a device that you're writing to. It's actually hardware. So you can write to some address or read from some memory, and what you're doing is actually accessing this hardware. And so this hardware will route that load, store, or move instruction to the device rather than RAM. The nice thing about memory mapped approaches is that now you don't need these special instructions. You don't need a finite number of ports. You can map anything to memory. As long as you can do that, you can be talking to I/O devices. Okay, so we'll finish up with a quick look at what's going to come up next. So in the next few lectures, we will take a look at file systems and take a look at how all of that works. A typical operating system is supposed to be able to handle many kinds of hardware. So it can have a hard drive, it can have an SSD drive, a flash memory system, it can have a USB interface to a flash device, so like think of a thumb drive with 2 or 32 or 128 gigabytes of memory that you plug into a USB port. And you have to handle the same kind, all of these different devices, but sort of the same way. You have files, you have folders, things like that. And so that's how you actually sort of pretend like all of these devices work the same way. So you use a file system and make it, and you say that this file system should work no matter what the actual hardware is. And so the key abstraction of storing data on these various very different devices, hard drives, USB drives, things like that, is that of a file system. And we pretend they just all work the same way, even though actually if you look at the hardware, they're very different devices. And so the crux of the problem now becomes how to build this device-neutral operating system. The operating system basically shouldn't care so much what the details of the hardware is. And we want to hide these details of these device interactions from some of the more important parts of the operating system kernel. And so here the key abstraction is a layer of software that can hide all of these details, and that's done with device drivers and file systems. And so device drivers keep a lot of the operating system device neutral. Sure, you'll need device drivers. You load them you load a different device driver depending on what the device is. So a USB drive will have a certain device driver as opposed to a hard drive, which has a totally different way of operating. But the device driver isolates most of the kernel, and the file system is actually a layer in this operating system kernel. We'll take a look at it in future lectures. So the device driver is really just software that knows the details of the device and sort of hides all of those details from the operating system. The operating system, it turns out in older operating system, you had to know exactly how hard drives were laid out, the exact geometry. We'll go into some of these details. You don't need that. That's just, it's much better to hide all of that. Sure, you might make the entire system a little bit less efficient, but it's much better overall. It simplifies the code of the operating system kernel to not know the details, and only the device driver really needs to worry about the details of the exact geometry of the device, how things are stored. And so on top of that device driver software is all of this stuff that has to do with the file system stack. So I just want to take a quick look, and those of you who've had networking, this might remind you of how networks are set up. You have this stack, and in the case of networks, it's the OSI stack typically, or the TCP/IP suite. In the case of file systems, you have something very similar. You have at the very top, you have the user mode application running. If it reads something from a file, you actually have to go through a bunch of layers. So the file system layer, and then has to go through a way of treating chunks of data no matter where it's stored, whether it's a hard drive or a USB drive. You use the term blocks, and typical block sizes are something like 512 bytes. Sort of similar to frames that we send out in networks, send out and receive. So that's the general idea, is that you use layers to simplify the design, so you can plug in a USB drive, and even though the actual geometry of the device, the way it's stored, is very different, you have these device drivers to isolate the overall system from all that gory detail. So in kernel mode, you have things like device drivers, the generic block layer. So that's something that's specific to Linux. And above that is the file system interface, the idea that you store things in files and folders or directories. All right, so those are the kinds of things that we will try to tackle partially next.